Hello everyone. So today we're going to be solving a problem from the European Physics Olympiad involving magnetics and specifically magnetic interactions between a long-form ideal solenoid and a perfectly circular Amperian loop when both of them carry certain currents. Okay, let's read it out. So a closed circular loop of radius r consists of an ideal battery of electromotive force, which has been given to us, and a wire of resistance r. So the wire of the perfectly circular Amperian loop, this one right there, has a total resistance of r. A long and thin air core solenoid, meaning that there's nothing such as soft core iron or anything to augment the magnetic powers of the solenoid. There's just air inside of that, is aligned with the axis of the loop, the symmetric axis, which is given to be z, and z is perpendicular to the plane of the Amperian loop. Its length is L, which is very, very great as compared to the radius of the circular loop, and its cross-sectional area is A. And A, as compared to the area of the loop, is very, very small. So they're talking about this cross-sectional area right there, this area, right? So the area of the solenoid is very, let's say it's negligible in terms of the variations of magnetic field inside of it. So that is going to help us make very reasonable approximations later on. The fact that that solenoid is very thin, meaning that its cross-sectional area is a very small quantity. And the total number of turns is n, and that helps us make another inference, which is that the number of turns per unit length is going to be given by the total number of turns divided by the length, meaning that the number of turns per unit length does not vary along the length of the solenoid, right? So that's the thing. The solenoid is powered by a constant current I, and we're doing this externally by an ideal current source. The directions of the currents in the solenoid and in the loop are the same, which for convenience we're going to be assuming clockwise, like that. Okay, and even in the loop it's clockwise. So we've been given all the necessary things, all the necessary variables for us to determine the magnetic interaction between the solenoid, the entirety of the solenoid, and the Amperian loop. Right. So I've been referring to the circular thing, this circle that's been placed at the edge. It's been called O1, right? The end of the solenoid, this end of the solenoid has been called O1, and the other end O2, right? So that's what we've been assuming. We've been assuming that the loop, let me highlight that loop. This loop, I've been calling repetitively the Amperian loop, the circular Amperian loop, and I'm going to be referring to this thing as the solenoid. Okay, so we're going to have to account for the magnetic interaction, the total magnetic force that exists between the solenoid and the circular Amperian loop. That's what the first part of the question is asking. And we're also asked to find the force F2 acting on the solenoid when its tail O2 is located at the center of the loop. So the first part is when the head O1 is positioned in the loop center O. And the second is when its tail O2 is located at the center of the loop. So they're going to be symmetric situations. You might speculate that the forces should be equal somewhat, maybe opposite. So let's see that. We're gonna be solving part A first. So there are multiple ways to go around this, but we're gonna be choosing the method that a multiplicity of thought processes are going to eventually converge to, right? So many people are going to be thinking this way. So, okay. Consider that Amperian loop, right? We know what the expression for the magnetic field is along its axis, right? And that is a standard result of the Biot-Savart law. It's basically mu n I r squared divided by 2 times r squared plus z squared, where z is essentially the distance taken from the symmetric point of that loop, right? Z squared and that thing raised to the power of 3 over 2. That is standard result. And since we've been given that the cross-sectional area of the loop, this area, is extremely small, as compared to the area of the perfectly circular Amperian loop, we may basically say that the magnetic field lines inside of the solenoid are do seem something like this, right? Equal everywhere. So we're going to be neglecting the variation of magnetic field inside of the solenoid. Okay, next thing. Now we have the magnetic field inside of the solenoid. How do we account for the total force on the solenoid after that? So, as we may know, every time a solenoid is broken down into elements, we do so assuming that the solenoid is made up of many Amperian loops, such as this, each of which may represent a dipole, right? So let's take an element dx, and I'm exaggerating that length so that we may imagine things in an easier way, and we might be inclined to think, let's just say that this differential length dx basically consists of n turns, let's say, and then this differential length dx of the solenoid will be associated with a certain magnetic moment vector given by dm, right? And how did I assume that direction? Well, we've been given the direction of current as clockwise, and you may use Fleming's right-hand rule. Just curl your fingers around the direction of current and you will obtain this. So is there any way we can link dm to dx? Well, by standard formula, we know that the magnetic moment vector, right, is given by NIA, right? This is standard expression. So the magnetic moment vector for any given circular loop with n turns, and current I is given perpendicular to the area vector, which we define perpendicular to the loop, like this, right? So in case of our scenario right here that we've assumed, the differential magnetic moment vector is going to be given by the total number of turns that is constituted within this dx length. And that would be given by the total number of turns divided by the length times dx. I hope you understand what we just did. N over L basically signifies the total number of turns per unit length, and we basically multiplied that by the length that we're considering. So we basically have the total number of turns in that dx length times I. The current has been given to us, and we were basically said that the solenoid has been powered by an ideal current source, times the area of the solenoid, and A is also a given variable. So congratulations, we've obtained the differential magnetic moment vector in terms of dx. Okay, so this magnetic moment vector should be subjected to some force, right? To some elementary force. We'll signify that by df, due to the magnetic field there. So now we'll take an alternative approach, which people might not necessarily be inclined to think of. We'll basically say that any Amperian loop, right, and we're basically considering a differential length dx along the solenoid, what we'll basically say is that this picture of a magnetic dipole is completely similar to two magnetic monopoles separated by that same distance, dx. We'll basically say that this is the North Pole, this is the South Pole. We'll basically say that their pole strengths are dm and dm respectively, and that they are under the effect of an external magnetic field B. So what do you think is the total force going to be in this picture? So in the second picture, right? In the second picture, the magnetic force is easier to write. The magnetic force is basically easier to write in the second picture, right? We'll basically say that that magnetic force is equal to dm times, let's say that the magnetic force, let's say that the magnetic field is basically B for the North Pole, and that it's basically B minus dB at that point for the South Pole, right? So magnetic field might not necessarily be uniform. So that's what we're assuming. At that differential length change, at that differential distance, the magnetic field varies as dB. So if there the magnetic field is B, then there that's B minus dB. Or you may take B at the South Pole and then B plus dB at the North Pole, but they're essentially the same thing. They're going to be yielding the same results. So yeah, we're going to be assuming, we're going to be taking into account the variation of the magnetic field along the length of the dipole. So we're basically going to say that the pole strength, dm, represented by dm, times the magnetic field, which is the force on the North Pole, minus the force on the South Pole, which is going to be given by dm times b minus db. Right? That is the net force on the dipole. Let's write a net in there. So the net force on the dipole is going to be given by the differential magnetic strength, magnetic pole strength at the poles, times dB. Okay, next we will translate between the two pictures. So the differential force on a dipole of length dx, of an actual dipole and not a loop model of the dipole, is given by this expression that we've derived just now. That same force is going to act on this Amperian loop model of the dipole with the same expression. The problem is we do not know how do we define a pole strength for this Amperian loop model. So we need another equation which can interrelate these two pictures, which is that the magnetic moment in this picture, in the first picture, magnetic moment in the first picture is defined as, by the way, it's a vector quantity. We're only concerned with the magnitude since we're only looking at things along the z-axis. The magnetic moment vector right here is defined, I think we defined it earlier, as n over L dxia. And the magnetic moment here, dm, in the second picture, is defined as dm is the pole strength times dx, right? Dx is basically that length that separates these things too. And there's an electrostatic dipole. The dipole in electrostatics has an analogy here to magnetic dipoles, right? The dipole moment vector is defined by the pole strength multiplied by the distance between the two poles. And that was basically our definition of the dipole moment vector, right? Where dx used to be a vector, but we're not treating things as vectors here. We're only just concerned with magnitudes. We may easily translate between the two pictures now, right? We'll use this equation and that equation to basically write dm in terms of the magnetic moment vector. So df is dm over dx times db, right? So two differentials on the left-hand side of the equation and two differentials on the right-hand side of the equation. This will just go multiply there, right? So that's the equation that we'll be using. We'll use that right there, right? So instead of using that expression for force, at which we couldn't really find the equivalent of the magnetic pole strength for the Amperian loop model, we'll just use this expression that we just derived. So the differential force is given by the differential magnetic moment vector divided by the differential length, dx, times the differential change in the magnetic field, right? So the differential force is given by And by the way, the expression that we derived earlier for the differential magnetic moment is actually proportional to dx. Look at this, right? So this dx and this dx right there, they'll cancel out, giving us something like this, right? So this is the equation that we're looking for. We basically solved part A. So that differential force is going to be given as N over LIA dB. If we integrate it, right, the limits of integration are from 0 to L, 0 to L. Actually, we should be doing negative L, but I don't think we should bother anymore. Well, because we're only concerned with the magnitudes. You can see that the limits of integration are from z equals to 0 to z equals to negative L, since this is the negative z axis. But we're just concerned with the magnitude, the total interaction force, right? And there are no other interactions, by the way, except for magnetic interactions, right? An element dx that we picked, basically, like this, is going to be, is it going to be attracted or is it going to be repelled? We'll also see if it's going to be attracted if it's going to be repelled, by the way, right? So if we've been given that the direction of current in the second loop is clockwise like this, right? It goes in and comes out from the top side. We've been given the direction of the battery, right? So the magnetic field is going to look actually like this inside of the solenoid. And if that is the direction of the magnetic field, that is also the direction of force that is going to be experienced by the elementary dipoles, right? So the solenoid is actually going to be attracted towards the loop. So it's an attractive force that the solenoid is experiencing, right? So but that might not be the case if we're evaluating F2, which is the force acting on the solenoid, if its tail is positioned at the center of the loop. We're working if O1 is positioned at the center of the loop right now. Let's just focus on that. We take that integral, so the net force of interaction is given by the total number of turns divided by L times A, right, B. The difference from 0 to L. So what is that difference? Right. Let's see what that is. B at 0 can be given from this expression, which is basically mu naught I over 2r, and B at L is also pretty simple, r squared divided by 2 times r squared plus L squared whole raised to the power of 3 over 2. So we've basically derived the total interaction force that exists So next comes approximations. We're going to be using this approximation that's been given to us. That L, which is the length of the solenoid, is very, very great as compared to the radius of the loop R. Actually, R is reserved for the resistance of the loop, so we'll be using a small r there. My bad. Switch that variable quick. So if L is indeed very, very large as compared to the radius, we may write that as L times mu naught I r squared. And actually this is 2 over. So, well, whether we're adding with r or not is basically irrelevant at this point. So we'll do this minus mu naught I over 2r, right? So we're basically using this approximation, and actually it's supposed to be solved using the binomial theorem. We should be converting stuff to this form, converting fractions to this form. 1 plus x raised to the power of n is approximately equal to 1 plus nx. This is the thing that we should be using, but we're using blatant approximations right now, right, in hopes of deriving the right answer. So since L is very, very large, this quantity reaches or tends to zero. So the whole thing simplifies to, we have two terms in current, by the way. So we basically assumed that the currents in the solenoid and the Amperian loop are both I, right? So this current I, right, let's call it I1. And this current in the solenoid, let's call it I, since that's the variable that's been given to us, right? So this is I, and that the other thing is I1, actually. I1. Okay. I1. I1. We've not been given I1. We've been given I1 in terms of the electromotive force and the resistance of the loop. So we'll be adhering to those variables. Mu naught times 2 times R. And so we'll basically say that that is E over R. I think that solves our problem for the interaction force. We've obtained a pretty neat expression. That is the answer for part A, right? The second part within part A deals with the situation whereby the solenoid is positioned such that its other end, O2, is at the loop center, right? So I think the expressions, the math is going to turn out the same way, right? The force is still going to be proportional to the differential change in the magnetic moment vector for every element dx, and we're basically going to be doing the same integral, right, using the same equations, and everything's going to be symmetrical, perfectly symmetrical. The question is whether or not the solenoid and the Amperian loop will attract each other this time, right? The other time, I think they attracted each other, right? They did attract each other. But this time, well, who knows? It might rather be a repulsive force, right? So, like the previous time, this is how the current is going to be, right? And that is going to produce a magnetic field in this direction. And we're basically assuming that there is no variation of the magnetic field throughout the solenoid, right? Has a length L. The magnetic, okay, since the solenoid's current is also clockwise, like this, right? Its dipoles are going to be given like this. So the net force on the dipole is along this direction, meaning that this time they will be repelled. They will be repelled. Repelled. So we may call this problem 8.2 and the previous one 8.1, right? The interaction forces are the same. It's basically a question of whether they're going to be attracted or they're going to be repelled. So we've basically solved part A for the problem, and part B, well, it's the same concept. We're going to be using the dipole moment concept again, that this thing is constructed out of, the entire solenoid is constructed out of many, many differential dipoles, but we're basically going to be saying that all of those dipoles cancel out. Since this is the direction of current, we'll basically say that this is north pole and this is south pole for a differential dipole, right? So this is how they're going to be composed. Sn, Sn, right? There's going to be many, 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 almost infinitely many number of dipoles composed that way. And all of the dipoles, almost all of the dipoles are going to be compensated for. They're going to cancel out like that. So the only ones that are actually going to remain are is this monopole right here, that's going to be signifying the north pole, and the monopole that's going to be signifying the south pole, right? At the two absolute ends of the solenoid. Those are the only two poles which we're going to be taking into account for part B. What does part B say? The solenoid is moving slowly with the constant velocity v. And now we've just calculated that the loop and the solenoid are either going to be attracting or repelling each other. So constant velocity v will require an external force, an external agency, ensuring that the velocity for the solenoid is constant. Along the z-axis, starting far away from the loop. Okay, the point O2, right? That's O1 starts very, very far away from the loop, very, very far, right? It starts from there, and O1, right? And O2 is just, again, very, very far. and it goes past its center and proceeds further to the right in positive z direction. We're going to have to plot the current J flowing in the loop as a function of time. And this time we have no electromotive force. It's basically an empty loop. We're going to have to use Faraday's induction law for this. Highlight the important features and values on the graph and velocity v. On the graph, and the velocity v is so small that self-inductance of the loop can be neglected. Meaning basically that the current that is induced is not going to produce a flux, right? So that's the Amperian loop. That's the Amperian loop I. This current is going to produce its own magnetic field around the loop, right? So we're basically going to have to neglect that. That is what they mean by neglecting the self-inductance of the loop. So let's think about this problem for a while. Let's draw a Amperian loop, right? Was that the direction? Was that the direction? Okay, I think I mistook the direction. This is the direction. This is the direction for the battery. This was the direction for the battery. Okay. So let's say that at any given instant of time, we basically have one end O1 of the whole solenoid at distance z. So we'll have the next thing at distance z plus L, right? O2. That's O2. And that's where the solenoid lies. Let's just say that, right? So we're going to have to somehow relate the velocity v of the solenoid that we're maintaining externally with the current that's going to flow in the loop, right? So if this thing comes closer and closer, we may speculate the magnetic flux increasing through this Amperian loop, right? We may speculate that it is increasing. So then, if the flux increases, in order to decrease the flux, the current is going to have to flow in this sense so that it has its own magnetic field B, right? In order to reverse that increase in flux, right? So that is going to be the direction of current. That's basically just a speculation. If things come out to be negative, we're going to have to assume the opposite as well, right? And as I said, we're basically only going to consider this pole right here as the North Pole, right? And again, point pole. And that point right there as the South Pole, right? So we're going to be considering the total flux phi through this Amperian loop, due to the North Pole and due to the South Pole. I don't know how they'll look like. I don't know how we'll draw the field lines, right? That all of that is basically just speculation. We know that the flux due to the North Pole is going to be positive, right? Meaning that it's going to go across like that. We're basically assuming this, the direction along the positive z-axis to be positive, right? So that flux is going to be positive. And due to the South Pole, it's going to be opposite, right? It's basically going to be opposite as that of the North Pole. And I think it's also going to be lesser in magnitude than the flux produced by the North Pole since it's farther away from the loop. So what exactly is the expression for flux, right? So I think we're going to have to make the diagram again. We're basically assuming that this length L is very, very long. This is our Amperian loop, right? Without a battery, with a net resistance of R. The solenoid still placed along its axis, moving with a velocity v. Here's its North Pole, here's its South Pole. And as I said, we're basically just going to be assuming the solenoid as a really, really long dipole, with its poles situated only at its ends, because all the poles at the middle are going to be compensated for, are going to be cancelled by each other, right? So that is what we're going to be assuming. So what is the flux due to this North Pole through this loop, right? So it's the same thing. It's the same thing. Let's assume that this is how the field lines are going to be coming out from the North Pole. It's going to be radially outwards and unaffected by the South Pole since the South Pole is so far away, right? Draw a sphere around the North Pole of an arbitrary radius z, and evaluate what the flux will be through this bulged part. Yeah, right, that subtends an angle theta. That is what the problem is. That is what the problem is basically saying when we say that we want to evaluate the flux that passes through this Amperian loop. Right, so so let's say that this Amperian loop subtends an angle of theta, right? And that theta is basically going to be cosine inverse of z, which is the distance for the North Pole, divided by z squared plus r squared, the root of z squared plus r squared, of course. That's given by the Pythagorean theorem. And we're going to be using this radius and drawing a sphere, right, around the North Pole. Let's say it's just a really big sphere, and then we're evaluating the flux through just this part, right? What is that going to be? So in simple terms, we're going to have to evaluate what this surface area A is, right? Let's call that A dash. And then that flux by the North Pole, in the Amperian loop is basically going to be that fraction, A dash over 4 pi z squared, which is basically a way of asking what fraction of the total area of the sphere around the North Pole of given radius is actually covered, by that bulged part through which we want to evaluate the flux, right? C squared plus R squared. That is what that is going to be, right? Times the total flux. The total flux is basically the total flux, by the way, the total flux throughout this sphere, actually, right? Just complete that sphere and evaluate that total flux. So let's calculate these things one by one. What is this area and what is the total flux? Well, we have an easy expression for total flux, right? It's actually the magnetic field B, which is same throughout the sphere. It's only a function of distance, and that distance is basically this radius, z squared plus r squared for that sphere, right? B times the area, which is 4 pi z squared plus r squared. Right, that is the total flux. So we may evaluate what B is easily. Mu naught over 4 pi times the pole strength at the North Pole, right, divided by, and we already know how to translate this pole strength in terms of other variables, right? How to transform this pole strength, which only exists in the actual dipole picture of a magnet, right, to the variables that are given to us in Amperian loop picture, right? Because we don't know what that pole strength is, right? But we know other variables that this pole strength is equivalent to, divided by z squared plus r squared times 4 pi z squared plus r squared, right? That is what that's going to be. So the total flux total, is going to be mu naught m over 4 pi z squared plus r squared. Actually, these things are going to be cancelled. Mu naught m over 4 pi times 4 pi again. Yeah, those things are going to be cancelled. It's basically just going to yield mu naught times m. And using the relation that the magnetic moment is given as the number of turns divided by L times dx times I times number of terms times dx times I times A, and also given as magnetic moment the pole strength times dx, right? We may basically just translate that thing. So the term that is equivalent to the magnetic pole strength is N over L times I times A in the second picture, in the picture for the Amperian loop model, right? So we're basically going to say that total flux is going to be given by Ni A over L times mu naught. So we're going to be we're going to have to take its fraction, right? And that fraction is A dash over 4 pi z squared plus r squared. So what do you think is A dash? So anytime we have a sphere, right, North Pole is situated at the center of it, and we want to calculate the area for this bulged part of that sphere, right, and right, you may draw a circle around it. It stands an angle theta. We're not going to be deriving that area, by the way. It's a result of standard integration. That area a dash is basically just given by 2 pi r squared, right? R here is the radius. We're not using r for that. We're using z squared plus r squared, right? R 2 pi r squared times 1 minus cosine of phi. That is that answer. That is the answer that we're looking for, right? So a dash over 4 pi z squared plus r squared, which is the radius of the total flux. That is the flux due to the North Pole. That is what we wrote initially as well. Let's simplify that. Z squared plus r squared, 1 minus cosine of phi. We'll write the expression for cosine of phi as well, right? We don't need to worry about that. 4 pi z squared plus r squared, and then total flux we've already written is NIA mu naught over L. That's the flux due to the North Pole. We cancel a few terms, and then we reach to this expression right there. Over L, 2L, 1 minus, what is cosine of phi? Cosine of phi is just z over the square root of z squared plus r squared, right? So it's just z over the square root of z squared plus r squared. That is the total flux due to the North Pole. The total flux due to the South Pole is going to look similar, but it's going to be opposite in direction, just opposite in direction, right? And we're going to have to add those two fluxes. So that's going to be, since it's at a distance z plus L, right? That is what that flux is going to be. Add the two flux, NIA mu naught over 2L, right? And if we do add it, we're basically going to get this thing. Z plus L whole squared plus R squared, and then minus Z over Z squared plus R squared, root of that whole thing. So we basically obtained the expression for the total flux passing through the perfectly circular Amperian loop. What that basically means is we can translate this expression to an induced electromotive force for the loop as flux changes. How is flux going to change? How's that flux going to change now? If you remember, the solenoid is being pulled or being driven by a constant velocity v, right? So obviously this variable z, which is the distance of the North Pole, is going to change, right? It's actually going to decrease, right? So that v may be said to be the negative derivative of z, right? V, in this expression, v is basically the negative derivative of z. If you think about it, v is basically, it's meant to be given as a positive quantity, but dz over dt, it's a decreasing quantity. So we're using this sign to, just be careful with the signs. We're just concerned with the magnitude. So yeah, the induced electromotive force around that Amperian loop is given as the time derivative of flux, actually negative of the time derivative of flux, but yeah, negative, positive, it doesn't really matter since we're only concerned with the magnitude. Again, we're only just concerned with the magnitude. So we're going to be using absolute value signs there to be absolutely just safe. Let's take the time derivative of this expression. The time derivative of the net flux through the perfectly circular Amperian loop is given as, let's take the derivative of the first function times the second function, minus the derivative of the second function L squared whole squared. I'm sorry. So it's going to be a monstrous expression, so let's have a bit of patience. Derivative of the second function times the first function divided by the square root of the second function. Minus the derivative of the second function times the first function minus the derivative of the second function, right, times the first function. Let's manage some space there. Times z divided by the square root of the second function again. z squared plus r squared. That is what that is going to look like. NIA mu naught over 2L times V, well, z plus L whole squared plus r squared divided by z plus L whole squared plus r squared, right? And that is going to yield something along the lines of derivative of the first function times the derivative of the second function evaluated at the first function, right? And then, well, we're basically just going to see this 2 times z plus L whole squared plus r squared, right? And then there's z plus L, that's just there. Okay, not much there. Minus, again, v z squared plus r squared over z squared plus r squared, right? And then plus 2 times derivative of the first function times the derivative of the second function, which is 2z divided by I'm sorry, actually. I think it simplifies down to this. Z times the derivative of the first function times the derivative of the second function divided by this thing. Okay. And we divide everything by z squared plus r squared. Okay. So it's a pretty monstrous expression that we have derived. Yeah, pretty monstrous, I should say. And yeah, we don't have a choice though. We don't really have a choice. What choice do we have? Nothing, right? So let's simplify it to L, right? That's going to be the induced EMF, magnitude of the induced EMF, right? V over z plus L whole squared plus r squared, the root of that thing, minus 2 times V, no, it's going to be something like V times z plus L whole squared divided by z plus L whole squared plus r squared 3 over 2 minus v divided by z squared plus r squared, right? I think it's going to be a 3 over 2 there, plus v times z squared divided by okay, this one, I think this one is going to be a 1 by 2, and that one is going to be a 3 over 2, right? So that is going to be the expression, monstrous expression. Let's simplify it further if we can, right? So this is going to be, v is going to be taken as a factor from all of them. We may basically say that that is 1 over z plus L squared plus r squared 1 over 2 minus z plus L over z plus L whole squared plus r squared 3 over 2 minus 1 over z squared plus r squared 1 over 2 minus z squared over plus z squared over z squared plus r squared 3 over 2. Okay, so that is the expression for the induced electromotive force on the perfectly circular Amperian loop as a function of z, which is the distance. And if we divide it by the net resistance, we'll basically have the current, right? So that is the expression for current. We've basically solved the problem.